Hello my friends, and welcome back to the You Can Do TV channel. At the rig site, two newbie workers are quickly learning the ropes and making the job look easy. Despite the harsh, fast-paced work environment, they handle heavy tools, pipe connections, and rig operations with impressive aplomb. Working under the supervision of experienced crew members, they move quickly, demonstrating teamwork and a high level of focus. Their duties include guiding drill pipes into position, operating tongs to tighten and loosen pipe connections, and assisting in the crucial process of moving pipes in and out of the borehole. It is a physically demanding job that requires strength, endurance, and constant attention to safety. One operates tongs to tighten or loosen joints, while the other prepares slips to hold pipes in place on the rotary table. When the drill bit needs to be replaced or a section of drilling is completed, the two work together to smoothly insert the new drill pipe into the mouse hole, align it, and connect it to the main pipe. Speed and precision are critical to not disrupting the process. Casing run begins by recovering the nominal seal protector and preparing the top drive system. Crews run casing in hole using 500T flush mounted slips and BX3 elevators with 15 bales. The casing is filled via a fill-up line while the stabbing guide and pipe racking system position the next stand. Frank's remote tong system with joint analyze makeup ensures proper torque. After landing the casing hanger, ROV confirms stable bullseye readings. Cementing follows, setting the seal assembly. Finally, the blowout preventer is tested before pulling out of hole. Roughnecking refers to the hard manual labor performed on the drill floor of an oil and gas rig. Roughnecks are essential members of the drilling crew, responsible for handling drill pipes, operating heavy mechanical tools, and ensuring the drilling process moves forward efficiently. The Roughneck's day typically involves tripping pipe, pulling drill pipe out of the hole, or running it back in. This happens when the drill bit needs to be changed, or when drilling reaches specific depths. Roughnecks use specialized equipment such as tongs, giant mechanical wrenches, slips, pipe clamps, and elevators, lifting devices, to maneuver and connect the heavy drill pipe sections. They also assist in making up, connecting, or breaking out, disconnecting, pipe connections. Roughnecks help maintain drilling fluid systems by operating the mud pumps, checking mud properties, and ensuring drilling fluids are circulating correctly. They also monitor safety-critical factors, like wellbore pressure, and help keep the rig floor clean and organized. Work shifts are long, usually 12 hours straight, often rotating between days and nights. Roughnecks operate in all weather conditions, intense cold, rain, heat, or storms, and must endure high noise levels, slippery surfaces, and constant physical strain. Safety is critical. Roughnecks must wear full personal protective equipment, PPE, including hard hats, safety glasses, heavy-duty gloves, flame-resistant clothing, hearing protection, and steel-toed boots. Regular safety meetings and drills are part of the routine to reduce the risk of accidents. Despite the physically demanding and hazardous nature of the job, roughnecking is often the entry point for a rewarding career in the oil field, leading to higher positions such as floorhand, derrickman, driller, and eventually tool pusher with experience and advanced training. The life of a derrickman on an offshore rig is both demanding and dangerous, working high up on the derrick or mast, often over 25 meters above the rig floor. The derrickman handles critical tasks, such as guiding and securing drill pipe as it moves in and out of the well. This role requires extreme focus, physical strength, and a steady hand, especially when balancing on narrow platforms in harsh weather conditions. Wearing full safety gear, the derrickman works closely with the driller and other crew members to ensure smooth operations. Mistakes are not an option. Safety is paramount. Despite the risks, many take pride in this high-skill position, knowing their work is essential to drilling success. Life on the rig is intense, unpredictable, and far from easy. But for a derrickman, it's all part of the job. At the Marine Discovery Center in Hamilton, Ontario, the Birmingham rig is carried out with great precision. A 30-meter-long pipe is lifted by crane and fed into the Birmingham Vertical Travel-Led Vertical Guide System. The rig is held vertically, ensuring precise positioning before the barrel is driven. The Birmingham diesel impact hammer is then activated, transmitting powerful force to drive the barrel deep into the ground. This method offers high efficiency, great stability, and is suitable for riverside and coastal projects that require high precision and strong bearing capacity of the foundation structure. Halliburton's CO2 frac job for prime up utilizes carbon dioxide to enhance oil recovery. CO2 is injected into reservoirs to increase pressure and stimulate production. This method improves efficiency, reduces environmental impact, and boosts recovery rates, making it a key strategy for maximizing output from mature fields. The 12-month process of building and tearing down a site at Cross Point in Lakewood, Colorado, involved several key stages, each impacting the surrounding environment in various ways. The initial pad build included moving in the conductor and drilling rigs to drill wells, followed by installing flow lines, casing, and conducting cement integrity testing. Once the wellbore was prepared, a tieback casing string was installed, and the frac operation was initiated, involving rigging up the necessary frac equipment. Post-frac, flowback was rigged up, and coil tubing and snubbing units were moved in to install downhole production equipment into well number 1. A similar process was carried out for well number 2. Following production setup, adjacent pad construction and reclamation were performed. The area outside the protective barriers was successfully reclaimed, and preparations for seeding the land for future use were completed. Throughout the process, careful attention was paid to minimizing environmental impact, with activities such as erosion control, waste management, and restoration of the area to ensure it could return to normal use. The comprehensive approach to site preparation, operation, and reclamation helped mitigate environmental effects, while ensuring the site was ready for post-production land use. At the Patriot Energy drilling rig site in the Permian Basin, West Texas, drilling is underway to a total depth of 8,100 feet. The process involves 3 crew shifts working around the clock, ensuring continuous operation in all weather conditions. The main operator on the rig, the driller, oversees the entire process, controlling the rig's operations and maintaining logs. One of the crucial components of drilling is the mud system, which serves to cool the drill bit and lubricate the drilling process. Drilling mud engineers monitor its circulation, as it provides essential data about the well's conditions. The rig uses large generators and a diesel engine to power the drilling operation. The drilling process involves adding 35-foot sections of pipe, which are connected using large tongs. The drilling continues until it reaches the target depth, with each section of pipe taking 20 minutes to 1.5 hours to drill, depending on the material being penetrated. Once the well reaches depth, the hole is flushed with water and the pipe is removed, a process known as cripping. Following this, the logging crew arrives to conduct a detailed analysis of the well's viability. With good logging results, the well proceeds to the completion phase, where production casing is installed and cement is pumped to secure the pipe in place, preparing the well for the next stage, fracking. After the production casing is installed and cemented in place, the well is left to cure before fracking begins. The next phase includes high-pressure hydraulic fracturing to release oil and gas from the surrounding rock. The Njord A platform was extensively upgraded at Aker Solutions' stored yard in 2016 and is now ready for another 20 years of operation. The upgrade aimed to ensure the platform meets production requirements and enhance its capacity to exploit nearby fields. Significant improvements include a 24% increase in buoyancy and a 31% increase in deck load capacity, allowing for additional equipment installation and the ability to accommodate production from the Fenja and Bausch fields. The platform is also equipped with new systems for drilling, control, and electrical power, improving efficiency and safety during operations. Notably, the platform is prepared to be linked to shore-based electricity via the Draugen platform, significantly reducing carbon dioxide emissions. The renovation project involved over 3,000 man-years of work and collaboration, with over 400 suppliers, with a total investment of 31 billion Norwegian kroner. These upgrades make the Njord A platform one of the most advanced and efficient offshore platforms, ready to maximize the potential of nearby resources and ensure long-term sustainable production. The comprehensive modernization not only enhances the platform's operational capabilities, but also supports Aker Solutions' commitment to energy efficiency and environmental responsibility. The Leviathan gas field, one of the largest offshore energy projects in the Eastern Mediterranean, showcases a monumental achievement in engineering and logistics. The Leviathan 3 and Leviathan 7 wells underwent extensive drilling and flow testing, followed by tree and pipe installation operations. Critical components such as production trees, umbilicals, and direct pipe shore crossings were manufactured and installed with precision. The project included the construction and float-out of both the cellar deck and production deck, supported by jacket roll-ups, sailaways and launches. Four massive vessels transported the topside units, which were ultimately installed by the world's largest offshore crane vessel in a record-setting lift of 15,300 tons. The Leviathan platform, standing 86 meters tall and resting in waters 86 meters deep, was built with contributions from 40 Israeli companies, and over 2,200 people worked on the topsides at peak. It took 26 months in collaboration across 24 countries to manufacture the platform's components. At a cost of $3.6 billion, the platform was successfully positioned in December, remaining on track to deliver first gas and supply natural gas energy to Israel and neighboring countries, a game-changing moment for regional energy independence. The production of premium base oil starts with crude oil, which is distilled to extract VGO-DAO fractions. These are fed into an iso-cracking reactor with hydrogen to break down heavy molecules. Light products like LPG, naphtha, and diesel are separated, while the remaining waxy lube oils go through iso-dewaxing to remove wax. The oil is then sent to a hydrofinishing reactor to enhance stability and clarity. Finally, the product undergoes a final distillation to produce various grades of high-quality base oils. Noble Energy has been operating in Equatorial Guinea for over 20 years, beginning with the Alba field, a major gas condensate field supplying Bioko Island. The Amco methanol plant, which started production over a decade ago, was the first project to monetize gas in the region. It efficiently converts raw gas into methanol, contributing to the local petrochemical industry. The Alba field remains one of the oldest and highest producing in the region, with the recent addition of the B3 platform extending its lifespan. This platform separates gas and condensate, with condensate being transported via pipeline to the Tsing FPSO. The gas is re-injected for future use, optimizing shipping efficiency and maintaining high production levels. Chevron unlocked the lower tertiary trend with the Jack and Malo projects, two of its largest oil and gas discoveries in the deepwater Gulf of Mexico. These reservoirs, located over 26,000 feet deep and under 7,000 feet of water, presented significant development challenges. Chevron tackled these with innovative technologies, including the enhanced single-trip multi-zone system, which allowed for efficient treatment and stimulation of the entire reservoir. Subsea boosting technology, essential for long-term success, was also deployed to maintain pressure and move hydrocarbons. The Jack and St. Malo floating production unit, the largest in Chevron's Gulf operations, has a capacity of 177,000 barrels per day. This project not only overcame technical obstacles but also set the foundation for future deepwater developments, unlocking new potential in the lower tertiary and expanding the Gulf's industry capabilities. Noble Energy and Ensign Drilling, using advanced drilling techniques, can drill 10 wells from a site half the size of a conventional rig. They supply 27% of the nation's natural gas and 14% of its oil, while minimizing the environmental impact, using only 0.07% of public land. The delivery of liquefied natural gas, LNG, involves a highly coordinated process to ensure safety, reliability, and efficiency. Modern LNG carriers like Asia Excellence are equipped with 4 insulated cargo tanks, each capable of holding up to 160,000 cubic meters of LNG. Before loading, the tanks are cooled and prepared to receive the cryogenic liquid. During transit, LNG is kept at -162 degrees Celsius, with continuous monitoring of temperature, pressure, and tank conditions. Onboard systems operate 24/7, and machinery is inspected regularly. Crews work across deck, engine, and cargo control to maintain stable operations. Detailed procedures govern every step, from loading and conditioning to voyage management and offloading. At California's Kern River oil field, smart technology and energy-efficient practices keep production above 80,000 barrels per day, over a century since its discovery. Techniques like steam flooding, 3D visualization, and digital oil field systems help extract difficult oil efficiently. Cogeneration plants convert steam heat into electricity, powering operations and feeding the grid. The construction and maintenance process of the Fluidized Catalytic Cracker, FCC, at Chevron's Richmond refinery is a massive logistical and engineering effort. The FCC, a critical unit in gasoline production, uses intense heat, low pressure, and a sand-like catalyst to break down hydrocarbons. Due to the extreme mechanical and chemical conditions, the unit undergoes scheduled maintenance to ensure safe and efficient operations. In preparation for the project, new FCC components were shipped from various parts of the country. One of the world's largest mobile crawler cranes was brought in on 160 trailer trucks and assembled on site. This crane, essential for the heavy lifts, required nearly 4 million pounds of counterweight across 106 units, each weighing about 38,000 pounds. The maintenance began with the careful removal of the old regenerator head and cyclones, which were lowered to the ground and placed in a cradle. Days later, the reactor head and its cyclones were also cut free and removed. Despite the ongoing work, the refinery continued operating at reduced rates. New components, including the reactor head and cyclones, together weighing over 750,000 pounds, were installed first. These were followed by the installation of a new combustor cone inside the regenerator. This cone plays a vital role in replenishing the catalyst used in the FCC process. The final major lift involved placing the new regenerator head and cyclones, which together weighed more than 1 million pounds. Water vapor emitted during this phase is part of the cooling system that recycles hot water to manage operating temperatures. Once complete, the revamped FCC resumed its critical role, producing nearly 10% of the gasoline consumed in Northern California. This project underscores Chevron's commitment to safety, efficiency, and energy infrastructure reliability. Automatic ultrasonic testing ensures weld quality by using ultrasonic waves. Before welding, UT technicians inscribe the pipe end for reference. After welding, the area must be free of any visible obstructions for accurate scanning. The UT bug, the scanning device, requires an anti-freeze solution to penetrate the weld during testing. This solution is collected in a sled and recycled for reuse. Inside the UT truck, the crew monitors the scan results in real time on a computer screen. Once the scan is complete, they remove the bug and proceed to the next weld for inspection. The CRC Evans copper backup clamp is a specialized electrical, mechanical, and pneumatic device designed for pipeline welding operations. Its main purpose is to clamp the pipe end securely and provide solid copper support for external root pass welding. The CBUC features a self-contained 24-volt electrical system, which powers the RF transmitter and air control valves. The main electrical components include a voltage meter, an Anderson plug located on the nose cone, and two 12-volt batteries mounted at the rear. The pneumatic system operates the clamping shoes, drive wheels, and brakes. It consists of a quick disconnect air fitting, pressure gauges, and two air tanks at the rear, one for brakes and clamping mechanisms, and a larger tank, up to 210 psi, for drive wheel movement. The system also includes an oil fog reservoir to lubricate pneumatic components, which should be checked and maintained at 6 drops per minute. The clamp moves through the pipeline using side-mounted drive wheels. It is operated via a radio frequency, RF remote control, allowing the operator to jog the clamp, raise and lower clamping shoes, apply brakes, and move the unit from joint to joint with auto travel mode. Before starting, the idler wheel assemblies must be properly adjusted to keep the clamp centered in the pipe. Installation involves lifting the clamp by its arm, positioning it rear end first into the pipe, retracting the brakes, raising the drive wheels, and jogging the clamp into position. The 4 primary steps of operation are aligning the copper shoes with the pipe bevel, aligning the pipe end, clamping the pipe and completing the root pass weld, and then auto-traveling to the next joint. Regular inspection, maintenance, and copper shoe replacement are vital for ensuring efficient, safe operation throughout the workday. The construction of an interstate natural gas pipeline is a complex, carefully managed process involving high-strength steel pipe, underground installation, and above-ground facilities like compressor stations and regulation equipment. A modern pipeline is built using a moving assembly line approach with specialized crews, heavy machinery, and strict environmental protections. Every stage is guided by experienced engineers and workers, meeting or exceeding government and industry standards for safety, environmental care, and reliability. Construction begins with clearing and grading a wide right-of-way, followed by trench excavation. Steel pipes, typically 40 or 80 feet long, are delivered, bent to match terrain, welded together by certified welders, and inspected using radiographic or ultrasonic methods. Once welded, the pipe joints are coated for corrosion protection. The sections are carefully lowered into the trench using side booms, cushioned with sandbags, and backfilled with soil. Hydrostatic testing ensures the integrity of the pipeline by pressurizing it above operating levels to detect leaks. After construction, the land is restored as closely as possible to its original state. Permanent markers are installed to indicate the buried pipeline. The right-of-way must remain clear of structures and deep-rooted vegetation to maintain safe access and operations throughout the pipeline's service life. The construction of the Wheatstone project followed a highly integrated and large-scale industrial process, beginning with early site development involving the preparation of roads, accommodation, and water infrastructure. Key fabrication activities were carried out at specialized yards in Tianjin, China, and Okpo, Korea. The platform topsides, one of the heaviest ever constructed, were jacked up 20 meters using 4 jacking towers to facilitate loadout onto a heavy lift vessel. Once the topsides were secured on the transport barge at full height, they were transported to the offshore location and precisely positioned above the steel gravity structure, SGS. Float-over installation was executed by ballasting the barge to gently lower the topsides onto the SGS. This precision operation ensured the platform's structural integrity and alignment on the seabed, 230 feet underwater. Parallel operations involve drilling and completing the Wheatstone and Lago gas wells using rigs such as the Atwood Osprey. Subsea infrastructure, including flow lines and spool tie-ins, was deployed to connect wells to the processing platform. Simultaneously, the onshore LNG facility was developed, including construction of LNG trains 1 and 2, installation of gas turbine generators, and the development of a materials offloading facility and LNG export jetty. A 140-mile subsea pipeline, weighing 340,000 metric tons, was laid to transport gas from the offshore platform to the onshore plant. The LNG plant's construction used approximately 320,000 cubic meters of concrete. After final hookups and commissioning, the plant began producing liquefied natural gas, with the first cargo loaded and exported shortly after. Throughout construction, emphasis was placed on safety, precision, and environmental management, resulting in one of the largest and most complex gas infrastructure projects in Australia's history. Life on the Hebron offshore platform, one of the world's largest, is unlike anything on land. As tall as a skyscraper and weighing over 750,000 tons, it stands 472 feet high and generates 98 megawatts of electricity, enough to power 50,000 homes. Located 211 miles from Newfoundland, it takes a 90-minute helicopter flight from St. John's to reach the rig. Personnel arrive wearing immersion suits to protect them from the frigid Atlantic waters. Workers stay on the platform for 21-day shifts, living in close quarters with up to 220 people on board. Most share rooms, and the rig runs its own laundry, washing around 3,500 pounds of clothes daily. There are kitchens, control rooms, game areas, and even satellite connections to families. With 198,000 eggs consumed annually, meals are no small operation. The crane handles massive cargo, from drill pipes to helicopter fuel. Hebron also has its own firefighting team and emergency life rafts that can be launched with compressed air prods. Digitally advanced and highly automated, The platform operates 24/7, supported by both offshore and onshore teams. Life is tough but rewarding, with a strong sense of teamwork and safety culture driving daily operations. In Cary, North Carolina, National On Demand uses the powerful JT20 directional drill by Ditch Witch to install fiber in a growing neighborhood. Their expert team handles the full process, from underground boring, trenching, and excavating to fiber splicing, testing, and long-term plant maintenance, ensuring fast, reliable connectivity infrastructure. The Fraste Multi-Drill Max is a powerful and versatile drilling rig, designed to deliver top performance across various drilling applications. It shares the capabilities of the basic Multi-Drill Max, but features an integrated Fraste manipulator for automatic rod loading, with onboard storage for up to 40 rods, 3 meters each. It is ideal for rotary drilling of water wells, geothermal projects, geotechnical surveys, seismic exploration, and core sampling. Its compact, modular design supports a wide range of drilling accessories. The rig allows easy switching between direct and reverse fluid circulation and supports DTH hammer drilling with a separate air compressor. In this operation, a cast iron pipe is being replaced using the pipe bursting method, starting from the basement wall. The R8 machine is set up in a horizontal configuration to handle the underground work efficiently within confined spaces. First, the crew cuts the old cast iron pipe close to the basement wall to create an entry point. After carefully removing any remaining fittings, the bursting head is connected to a new section of high-density polyethylene, HDPE pipe. The R8 bursting unit, aligned horizontally, provides the pulling force needed to guide the bursting head through the existing cast iron pipe. As the bursting head moves forward, it fractures the old pipe, pushing the broken pieces into the surrounding soil. Simultaneously, the new HDPE pipe is pulled into place, seamlessly replacing the old line without the need for extensive excavation. Throughout the process, precision is crucial to avoid damaging nearby utilities or the building foundation. The setup involves using a strong steel cable or rod system attached to the R8 machine, ensuring a continuous and controlled pull. Once the bursting operation reaches its exit point, the crew disconnects the bursting head, connects the new pipe to the existing plumbing, and thoroughly tests the line for leaks and integrity. The final step is to clean up the area, restoring the basement wall penetration and ensuring the system is ready for use. This method is particularly advantageous because it minimizes property disruption, reduces project time, and results in a new, durable pipe installation with minimal surface impact. The R8's horizontal setup provides the necessary strength and stability for a smooth, successful burst, even in challenging residential environments. The Propel Frac Blender is built for modern fracking needs with dual C18 Cat engines providing 1,600 horsepower. It features a high-capacity cube radiator for efficient cooling, a patent-pending two-piece manifold with hardened steel inserts for longer lifespan, and an oversized sandhopper that holds up to 3 yards of material. The blender also includes hydraulically operated augers, a user-friendly operator cab with sunshade and easy access to controls, and optimized fluid dynamics for superior mixing. Designed for durability and performance, it ensures high reliability and easy maintenance, making it an ideal choice for continuous, high-demand fracking operations. The record-breaking 48 inches direct pipe project was designed by Arsenault Wilson & Cole and geoengineers, connecting the city of Port Arthur to Pleasure Island. The project installed a 48 inches steel casing and a 30 inches HDPE pipe over a 3,500-foot distance, running beneath the U.S. Army Corps of Engineers Hurricane Protection Levee and the Sabine-Neches Canal. Completed in 2015, it was the longest direct pipe installation in North America at the time. The German-designed Herrenknecht direct pipe technology was selected instead of traditional HDD, as it better controlled drilling pressure and minimized ground fracture risks. A 750-ton hydraulic pipe thruster pushed the pipe as a microtunneling machine excavated the bore. Despite the narrow working space between a highway and residential area, drilling reached an average speed of 6 feet per hour, peaking at 20 feet per hour. Strike Construction and Laney Directional Drilling handled the operations. After 29 days of non-stop 24/7 drilling, the breakthrough occurred precisely as planned with minimal surface disruption. The installation of the 30 inches HDPE carrier pipe followed immediately. The entire project, from approval to site restoration, was completed in less than 5 months, well ahead of the 180-day contract period, demonstrating Arsenault Wilson & Cole's expertise, innovation, and commitment to engineering excellence. Hobus Trenchless Sewer Rehabilitation, led by Michel Bau, offers a highly efficient solution for aging sewage systems in major cities. In Cologne, Germany, Michel Bau demonstrated its expertise by renewing a 100-year-old sewer network without major surface disruption. Their method uses stereoscopic measurements to design the largest possible GRP, or HDPE pipes, inserted precisely with special installation trolleys. Pipes are connected by durable spigot and socket joints, then secured and grouted with special concrete to stabilize the old structure. This fast, trenchless system minimizes environmental and economic impact while ensuring long-term reliability. Michel Bau's technology meets the highest international standards, making them a trusted partner for cities seeking sustainable sewer rehabilitation at the highest technical level. Horizontal directional drilling, HDD, is a fast and efficient trenchless method used for fiber optic cable installation under roads and other obstacles. The process begins with preparing entry and exit holes, followed by mixing a special cooling solution to protect the drill head from overheating. Next, the coring machine is positioned at just the right angle, and the surface-launched drilling rig is set up. As the drilling starts, coolant is continuously pumped through the system, and drill rods are added dynamically to extend the reach. The rig generates more than 4 tons of pushing force to drive the drill head through the subsurface. Once it emerges on the other side of the road, the drill string is prepared for the next phase. A fiber holding pipe is then attached and pulled back through the newly drilled hole using a pulling force of over 13 tons. The entire operation, including setup and pullback, is completed in just over an hour, minimizing surface disruption and traffic interference. The sewer system in Germany has around 10 million manholes, with approximately 1 million needing rehabilitation due to corrosion, groundwater infiltration, and defective connections. One example involved a 1,200 mm concrete manhole near Halle that had suffered severe hydrogen sulfide corrosion. To rehabilitate it, a Hobus shaft-in-shaft solution was chosen. This method involves inserting a one-piece GRP, glass-reinforced plastic, Hobus liner into the existing structure, requiring minimal demolition and avoiding costly excavation. After removing the superstructure and cleaning the site, the lightweight, prefabricated GRP liner is lowered into place, aligned, and connected to the existing pipes. Short pipe sections bridge the gap between old and new structures, sealed with GRP laminate for a watertight and durable bond. Liquid grout is poured into the annular space, bonding the structures permanently. The final steps include reconstructing the superstructure and restoring the road surface. Hobus liners are highly corrosion-resistant, structurally stable, watertight, and low maintenance. They are quick and easy to install, even in deep manholes, and require only light construction equipment. Variable diameters and channel shapes are available, allowing flexible installation in a variety of settings. In this case, the Hobus one-piece liner proved to be a cost-effective, long-lasting solution for manhole rehabilitation, ensuring minimal disruption, maximum safety, and reliable performance over decades of use. Trenchless pipe rehabilitation is a modern method used to restore aging or damaged pipelines without the need for extensive excavation. One widely used technique is swage lining, which involves inserting a high-density polyethylene HDPE pipe into an existing pipeline. The process begins with cleaning and inspecting the host pipe to ensure it is suitable for rehabilitation. A reduction die is then used to temporarily reduce the diameter of the HDPE pipe, allowing it to be pulled through the old pipe with significant pulling force, often exceeding 100 tons in large diameter applications. Once in place, the pipe returns to its original shape, creating a tight fit within the host pipe and forming a corrosion-resistant, long-lasting lining. This method minimizes surface disruption, making it ideal for use in urban areas or environmentally sensitive locations. Equipment and systems are thoroughly checked before operation to ensure safety and efficiency. Trenchless rehabilitation extends the lifespan of pipelines, while reducing costs and environmental impact. The Pipe Ram by Roddy Underground is a trenchless boring system designed for precise underground pipe installation beneath surfaces, such as sidewalks, driveways, and roads. The process begins by preparing the job site and excavating entry and exit pits if needed. The pipe ram unit is then positioned securely in the entry pit, connected to a hydraulic power source, typically supplying 6 to 20 GPM at 3000 psi. Solid push rods or 2-foot steel pipes are attached to the front of the machine. Once activated, the unit generates powerful thrust to push the pipe through soil with precision. Operators continuously add pipe segments or rods as needed, pausing between strokes to connect each section. Direction can be monitored using a locating device, like the Vivax VLOC3, to ensure accuracy. ramming continues until the pipe reaches the target point, or exit pit. The system is highly effective for installing conduits without surface disruption. After the bore is complete, the machine is disengaged and removed, and the entry and exit pits are restored. This method offers a clean, efficient, and low-impact solution for underground utility installation, making it ideal for urban environments or areas where surface disturbance must be minimized. Pipeline drillers successfully completed the pullback phase of a horizontal directional drilling HDD operation for the Microtunneling Rising Main Upgrade project. In this project, a 630 mm high-density polyethylene HDPE pipe was installed over a distance of 347 meters. The pullback process involves drawing the pre-welded pipeline through the previously drilled borehole, using a specialized drilling rig. The HDPE pipe, prepared in advance, is carefully guided into position as the drill rig applies steady pulling force. Precision is crucial to prevent bending or damaging the pipe. The video highlights the coordination between ground crew and machine operators, ensuring smooth insertion. This trenchless technique minimizes surface disruption while delivering efficient and long-lasting pipeline installation. In a record-breaking trenchless installation beneath the Spree River in Germany, Agrelin high-density polyethylene HDPE pipes were used to create a large-diameter twin-pipe culvert. The project involved two parallel horizontal directional drilling (HDD) bores, each 220 meters in length. One bore accommodated a 1,400 mm diameter SDR-17 PE pipe, and the other, a 1,200 mm diameter SDR-17 PE pipe. This pioneering installation marked a global first for HDD at this size and scale. The pipes were manufactured by Agro Kunststofftechnik and supplied by Frank. The trenchless work was carried out by Visser and Smit Hanaab, a Dutch contractor highly experienced in HDD technology, acting as a subcontractor under Trap Infra Rohrbau Welsau GmbH. Commissioned by Vattenfall Mining Europe, the installation was completed between March 9 and March 22, 2016. The use of HDD avoided significant environmental disruption and showcased the feasibility of installing very large diameter PE pipelines using this method. This project not only demonstrated technical excellence, but also set a new benchmark for sustainable pipeline installation beneath sensitive waterways. Roddy Inc. UB40 Microtunneling Machine presents a groundbreaking trenchless solution for small diameter pipe installation, especially suited for sewer replacements in residential communities like Milpitas 400-unit Mill Pond Mobile Home Park in San Jose, California. Traditionally, such projects require disruptive open-cut trenching, but Roddy's innovative system eliminates the need for surface excavation. The process begins with detailed surveys of utilities, trees, and pavement to minimize disruption. Two vertical shafts are sunk up to 200 feet apart, and a pilot tube is pushed horizontally between them. Using a theodolite and camera system, operators steer the pilot tube with precision, up to 1/8-inch accuracy over 200 feet, by rotating its slanted tip to align the lighted target with crosshairs on a screen. Once the pilot tube reaches its destination, it is removed and replaced with a pulling head attached to the product pipe. As the pilot tube is withdrawn, the pipe is simultaneously pulled into place through the tunnel. Roddy's microtunneling is environmentally friendly, reduces site restoration costs, and provides a reliable, proven alternative to traditional sewer installation methods. In September 2016, the Trans-Adriatic Pipeline TAP project reached a key construction phase near Alexandroupoli, Greece. Captured from above, this licensed footage reveals the pipeline construction process in a linear, efficient sequence. It begins with clearing and grading the easement, preparing the land for safe and stable installation. Next comes stringing, where steel pipes are laid out along the route, followed by bending to match terrain contours. Welding teams then fuse pipe sections together, with every weld undergoing strict X-ray or ultrasonic testing to ensure structural integrity. After testing, each weld joint is carefully coated for corrosion protection. Finally, trenching crews dig and prepare the path to lower the pipeline into the ground. This meticulous process reflects TAP's commitment to safety, quality, and environmental responsibility throughout construction. In Pecos, Texas, TechCore is actively involved in a pipeline construction project, showcasing a precise and well-coordinated process in collaboration with industry partners. The operation begins with clearing the right-of-way to make space for equipment and materials. Once the path is cleared, pipe transport, stringing, and assembly follow, laying out the pipes along the route and preparing them for connection. Trenches are then excavated to accommodate the pipeline. After placement, pipe fitting ensures alignment and positioning. Next comes automated girth welding, creating solid pipe joints, followed by weld buffing to smooth the surface. Real-time radiography and ultrasonic testing provide immediate feedback on weld integrity. These non-destructive testing methods are crucial for quality assurance. Post-inspection, welds are sandblasted, prepped, and coated for corrosion protection. Finally, the coated pipeline is lowered into the trench with precision, and the entire trench is carefully backfilled to secure and restore the ground. This efficient process highlights TechCore's commitment to safety, precision, and pipeline reliability.